Welcome to another module in this massive open online course on principles of probability and random variables for wireless communication. Alright. So, in the previous module we have seen the concepts of conditional probability. Let us now look at another aspect, another very important property that is known as independence. Alright. So, today let us look at the concept of independent events, and this is a very important aspect of probability. That is, let us define this. This is a very key concept in probability. We say two events are statistically independent. Two events are statistically independent if the probability of A given B, that is two events A and B are statistically independent if the probability of A given B equals the probability of A equals the probability of A. That is, what are we saying? That is the probability of A given B. That is, we say two events A comma B. Let me clarify this. Two events A comma B are statistically independent if the probability of A given B or the probability of A conditioned on B is simply the probability of A. That is, given that event B has occurred does not in any way affect the probability of occurrence of A. We say that A and B are independent if given that B has occurred does not in any way affect the occurrence of probability of A. Therefore, the probability of A conditioned on B is simply the probability of A because it is unaffected. So, let me again write this. So, probability, this implies probability of occurrence of B has no effect, that is occurrence of B, has no effect on probability of occurrence of B has no effect on the probability of occurrence of A. Therefore, we can say in that scenario we can say A and B are independent. Let us simplify this further. So, we say that A and B are independent if probability of A given B is equal to the probability of A, but we have also defined probability of A given B as probability of A intersection B divided by the probability of B implies probability of A intersection B divided by the probability of B equals probability of A, which implies the probability of A intersection B equals the probability of A times the probability of B, right. So, the probability, which if you can see this is a very important probability. So, for independent events A comma B, the probability of A intersection B, that the probability that both events A and B occur is simply the product of the probabilities A and B. So, the product, so the probability both A comma B occur is simply equal to product product of probabilities of A, that is the probability that both A and B occur, that is probability of A intersection B is simply probability of A times the probability of B if A and B are independent. That is the probability that both events A and B occur is simply the product of the probabilities of events A and B. Similarly, one can also define independence the other way, that is the probability of, now similarly let us start with this probability for independent events. We have probability of A intersection B equals probability of A times the probability of B, which basically implies that the probability of or the probability of A intersection B divided by the probability of B is equal to the probability, or divided by the probability of A is equal to the probability of B, which also implies that the probability, this probability of A intersection B divided by the probability of A is nothing but the probability of B given A is equal to P of P. Therefore, if A and B are independent, we have said that the probability of A given B is equal to the probability of A. Similarly, we have also derived from that property that the probability of B given A is equal to probability of B, right. It works both ways. If A is independent of B, then B is independent of A. Therefore, we can say now that the condition for independence is that the probability of A given B is equal to the probability of A or both, and that also implies that the probability of B given A equals probability of B. This is if A comma B are independent, if A comma B are if A comma B are independent events, we said we are saying that the probability of A given B is equal to the probability of A, probability of B given A is equal to the probability of B, and further probability of A intersection B is simply equal to the probability of A times the probability of B. Alright, this is a simple technical definition of the of independence, and intuitively we have also said that this means that the occurrence of event B has no bearing on the probability of occurrence of A. Also, the occurrence of event A has no bearing on the probability of occurrence of event B. That is when events A and B are independent. Okay. Let us look at an example. Let us prove an important property as an example. If A and B are independent, show that A comma B complement are also independent. That is, if two events A and B are independent, then we want to show that A and B complement are also independent. That is, the event A is also independent. That is, if event A is independent of event B, then we want to show that event A is also independent of the complement of event B. And this can be seen as follows. For instance, we are already seen yesterday from a pictorial, from a diagrammatic representation, we had already seen yesterday that if we have two events A, if we have two events A comma B, this is the region A intersection B, and this is the region A intersection B complement, and you can see that A intersection B complement and A intersection B are, as we had seen yesterday, these are mutually exclusive. We can see that the intersection A, that the events A intersection B complement and A intersection B are mutually exclusive, that is their intersection is the null event. Further, the union of these two events is the event A, right. So, A is equal to A intersection B complement union A intersection B. Therefore, using the third axiom of probability, we can write probability of A equals probability of A intersection B complement plus the probability of A intersection B. However, we are given that A and B are independent, therefore, we have probability of A intersection B is equal to the probability of A times the probability of B. Therefore, now using this property, we can say, substituting this property over here in place of probability of A intersection B, we have the probability of A equals probability of A intersection B complement plus probability of A times the probability of B, which implies the probability of A intersection B complement equals probability of A minus probability of A times probability of B equals probability of A times 1 minus probability of B. And now you can see that basically 1 minus probability of B is nothing but the probability of B complement, which basically implies probability of A intersection B complement equals the probability of A times the probability of A times the probability of B complement. Therefore, what we have demonstrated is that given A and B are independent, we are able to show that probability of A intersection B complement is equal to the probability of A times the probability of B complement. Therefore, A is also independent of B complement. Remember, the condition for independence is the probability of the intersection or the probability of the joint event is equal to the product of the probabilities of the individual events. Therefore, we have shown that since probability of A intersection B complement is equal to probability of A times the probability of B complement, A is independent of B complement as well, if A is independent of B. So, this shows, this implies A is independent of B. So, this shows that A is independent of B complement. Okay. Let us look at another example. Let us go back to our Emery-PSK. Let us look at an example of Emery-PSK to understand this. I am sorry, Mary-PAM. Remember, we are looking at Mary-PAM, where M is equal to 4, PAM stands for pulse amplitude modulation. Our sample space is minus 3 alpha, comma minus alpha, comma alpha, comma 3 alpha, and I have the probabilities 1 by 8, 1 by 4, 1 by 4, 1 I am sorry 1 by 8, 1 by 8, 1 by 4 and half. So, we are looking at an Mary-PAM constellation pulse amplitude modulation with m is equal to 4. I have the symbols minus 3 alpha, minus alpha, alpha, comma 3 alpha. The probabilities are 1 over 8, 1 over 8, 1 over 4 and half respectively. And let us also look at the events A, which we have already defined previously. A is equal to minus 3 alpha, comma alpha, and B equals simply the event alpha corresponding to the symbol alpha. Now, let us ask the question, are A comma B are events A comma B, are these events independent? So, let us use our definition for independence. So, we have defined A as the event corresponding to observing, similar to what we had done before. A is the set, A is the event minus 3 alpha containing the sample points minus 3 alpha comma alpha. So, A basically corresponds to observing the symbols either minus 3 alpha or alpha, and B, the event B, corresponds to observing the symbol alpha. And therefore, now we are asking the question, are these two events independent? Let us use our definition of independence to check if these two are independent. Now, we have probability of A, which we have already derived before. Probability of A is simply the probability of minus 3 alpha comma alpha, which is equal to 1 by 4, or which is equal to 1 by 8 plus 1 by 4 is equal to 3 by 8. Probability of B is equal to the probability of simply the single sample point alpha, which is equal to 1 by 4. Therefore, the probability of A intersection B, therefore, the probability of A times probability of B equals 3 by 8 times 1 by 4, which is 3 by 32. Now, let us look at the event A intersection B. A intersection B is simply minus 3 alpha comma alpha intersection alpha, which is basically the single sample point alpha. Therefore, probability of A intersection B equals simply the probability of alpha, which is equal to 1 by 4. Now, you can see the probability, now you can see from both of these, this is probability of A times probability of B, this is probability of A intersection B. Now, you can see probability of A intersection B is equal to 1 by 4, which is not equal to the probability of A times the probability of B, which is basically equal to 3 divided by 32. So, we are saying that the probability of A intersection B is 1 by 4, probability of A times the probability of B is basically 3 divided by 32. Therefore, the probability of A intersection B, that is the probability that both events occurring, is not equal to probability of A times probability of B, that is the product of probabilities. Therefore, A and B are not independent. Therefore, we are saying something interesting. Therefore, A and B are not independent. Therefore, A and B are not independent events, and this is also natural because A is the symbol minus 3 alpha or alpha, right. A denotes the events observing the symbols minus 3 alpha or alpha, B denotes observing the symbol alpha. Therefore, if one has told you that he has observed B, that is, he has observed symbol alpha, then definitely you can conclude that event A has happened, because event A is either minus 3 alpha or alpha. So, given B conveys a lot of information about event A. In fact, given event B has occurred, one can conclude that event A has definitely occurred. Therefore, observing event B has an effect on observing on the probability of occurrence of A. Therefore, B and A are not independent. Remember, what we are saying is B, our A equals minus 3 alpha equals observing that is, or symbol minus 3 alpha or alpha. B equals, let us put it, the set A basically says that the symbol equals minus 3 alpha or alpha, and B symbol is equal to basically alpha. So, if one has told you that B has occurred, that is alpha, as the symbol is alpha, so definitely A has occurred, that is the symbol is either minus 3 alpha or alpha, and therefore occurrence of B has an effect on the occurrence of A, or B affects the probability of occurrence of A. Therefore, by definition they are not independent. So, therefore, we can say that probability, and remember we had seen this previously, probability of A given B equals 1, which is greater than the probability of A which is equal to 3 by 8. Therefore, probability of A given B is not equal to probability of A, which basically also again implies A comma B are not which basically implies that A comma B are not independent. Similarly, probability of B given A is equal to 2 by 3rd, which is greater than the probability of B which is equal to 1 by 4. Therefore, probability of B given A is not equal to the probability of B, which also basically once again implies that A comma B, which also implies that all of these imply the same thing, A comma B are not A comma B are not independent, correct. So, this is the key aspect here. That is what we are saying is these two events A comma B, where A denotes the event containing the sample points minus 3 alpha and alpha, B denotes the event containing the sample point alpha. These two events are not independent, because the occurrence of one has an effect, has an impact on the probability of occurrence of the other. Given that B has occurred, has an impact on the probability of occurrence of A. Given that A has occurred, has an impact on the probability of occurrence of B. Therefore, A and B are not independent. We have also verified this through using our definition of independence, that is the probability of the joint event probability of A intersection B is not equal to probability of A times the probability of B. Therefore, these events are not independent. Okay. We will look at some other examples of independence in the subsequent module. Let us stop this module here. Thank you very much.